So it's a great pleasure to welcome Peter Petersen from UCLA, who will speak on rigidity of homogeneous gradient soliton metrics and related equations.
Yeah, and thanks for inviting me. I guess I can't even keep track of what time zone people are in right now. It must be like all over the place, since I don't know where everyone is at the moment either. We've actually had several faculty who stayed in Europe for the pandemic, so I don't know how you can teach with a 9-hour time difference, but they seem to have done that very well. So at least I'm here at the right time, which was the main thing for me. Yes, Will and I, we've worked on this. Okay, now good. Okay, I just had to get rid of a thing from Zoom there. And it was actually something we started exactly 2 years ago down in Brisbane. So that was the project that we were going to get this started, and we finally finished it last summer. And well, things are not moving fast these days, so it's still not published. But it is. The paper is on archive. So let me tell you what this is about. Let's see if I can do this right here. There we go. Carolyn, you might have heard this because Will gave this similar talk at Dartmouth, I think, a while ago. So it's going to be similar to that. We're going to look only at complete metrics, Riemannian manifolds. And I'm just going to start by giving some facts from the past that will help you understand some of the things that will happen here. So first, there's a version of de Rhams theorem. I think maybe it's not quite de Rhams theorem. It's more elementary than that, but that's what we agreed on. So if you have a non-constant function whose Hessian is 0, then the manifold has to be a product. And you can factor off, this is where the de Rham thing comes in, namely you factor off the de Rham factor as Rk, and then the function f is a linear function on Rk. So normally you would just factor off one real line from the function, as in the splitting theorem. But if you use de Rham's theorem, you can see you get a little more structure, if indeed there's more factorization. So that's a fairly obvious sort of thing to do. And maybe a little less obvious is this theorem by Obata 10 years later. If you have a non-constant function on a, well, let's take a compact manifold just to be safe, but it's not necessary to assume that in this case, such that the Hessian is a negative multiple. So that's why you have minus c squared of the function u times g, okay? So you can see it's supposed to look kind of like an eigenvalue problem, except you have the whole Hessian instead of just the Laplacian here, right? So if indeed you're looking here at Laplacian instead, right, then this is just going to be an eigenvalue thing you have here, right? They are always negative if you use that, well, the usual convention in geometry like that. So then the manifold has to be a constant curvature sphere, and U will be the restriction of a linear function from the ambient Euclidean space to the sphere. Okay, so in other words, it's an eigenfunction because that's what eigenfunctions look like. They're restrictions of linear functions. So the idea is that if you have a function and its Hessian is proportional to the metric or conformal to the metric in a suitable sense, that then you get a lot of rigidity. And this has been investigated by lots of people. It goes back to Brinkman in 1925 already. And Tashiro, he did the complete case. Brinkman stuff was more local. And Osgood Stobe, they related it to some other issues and also did this, studied this in detail in 92. So let's get to what I want to study and get out of this. So first of all, these are just sort of the basic examples of what I want to look at. So we have gradient Ricci solitons, and they are just manifolds where you have a function such that the Ricci curvature plus the Hessian is a multiple of the metric. And these are self-similar solutions to the Ricci flow, right? So they've been studied quite a lot. So you can see that we also have some of the other things that appeared in Obata's theorem. A conformal Einstein metric, that's a Riemannian manifold with a function W, non-zero function, such that the traceless Ricci tensor, so this circle that I use here in both cases just means you're subtracting the trace out, so you have a traceless equation, okay? So you can always do that. So the traceless Ricci curvature is some, well, negative constant 2 minus the dimension over W and times the traceless Hessian, okay? So this means you don't have a Laplacian anymore. If you trace this equation, it's just a 0 equals 0, okay? And so what you really want to do is you probably want to take this W and put it on the other side to make it look a little nicer. This is the equation that the simplest possible equation that tells you that in a conformal class, you have to have an Einstein metric. So I'll have more to say about that later. So now what I want to do is, instead of looking at these concrete examples, which people have studied quite a lot, we wanted to sort of abstractify what it is that goes on in these equations to see what the essence is. Is the Ricci curvature really important in these equations that you had here? Right, that's the question. Or is any tensor good enough? Well, not just any tensor, of course, because then you could always have these equations work. So that's what I want to look at. So we're going to look at, well, 4 types of equations, but only really 2 types. So we have the Hessian is equal to some tensor Q. So that's like the gradient soliton equation. And the Hessian is equal to W times the tensor Q, okay? So you can see here there's no W and there's a W, right, or F. And then you can look at the similar traceless equations, okay? So the traceless equations look much more general, but will actually show that either they are equivalent to one without a trace, or they're even more special than you might imagine. So, which is interesting also. So just to start, we'll go back in time to, actually, I think this is Will and My's one of our first papers. So if you take a homogeneous gradient soliton, then it's isometric to a product, and F is a quadratic function on the Euclidean factor. So you see very close to that Theorem thing I had earlier on, okay? So here, the key is that it's homogeneous, okay? So that's a strong assumption to make. And that's what I want to study. I want to study these equations here when the manifold is homogeneous, and the metric is also invariant under this isometry group. So if you think of Q as being the Ricci curvature, that's always going to be invariant under any isometry, right? And that's all I want to assume. So this is what we're going to do. We'll, instead of looking at just one solution, so when you have an equation like this, right, you could just focus on one solution, but it's easier actually to just look at the space of all possible solutions. So we'll look at, we'll fix Q, and we'll look at all the functions whose Hessian is equal to Q. And that you can do without any assumptions. Now, then if you take an isometry on the underlying manifold, such that Q is invariant under that isometry, then you can see that any function will be mapped to, when you pull back by the isometry, another function that is also part of this space of solutions. So that's because the Hessian has to be invariant under isometries. And so if Q is also invariant, then when you pull back F, then that has to be a solution to the equation, right? So F is not a vector space, but it is an affine space, so that if you subtract two elements of it, then the difference will lie in the vector space of functions whose Hessian is 0, right? So you can see if you subtract two of these items there, right, then the Q's cancel, and you get this vector space of solutions where the Hessian is 0. And of course, that space it gives you rigidity, right? So B is then a vector space, and of course the constant functions are in there, so you have to be a little careful with that. But if the dimension of V is bigger than 1, then you will have some non-constant functions, and then you can use the Theorem theorem to see you have to be a product, and it has to be a product where the R factor corresponds precisely to the dimension of W, right? Because that's how many linear functions you have if you add the constant function as well, right? All right. So now the question then, what happens is if the dimension of V is equal to 1, because that's the case where you can't do anything. You only have constant solutions, and that doesn't tell you very much. So, but then you get a different type of rigidity because of that. So for each, so you take each isometry, and then when you pull back the function, well, if you look at the difference, right? Now the difference is supposed to be in the vector space V, which is one-dimensional, so it has to be a constant that depends on the isometry, right? So in that way, you get actually a group homomorphism from the group of isometries onto the real line, and that could give you some special things too. Now you do want to make sure, though, of course, that again that the Q is invariant, right? It's like that. Okay, so let's take a manifold then that has a transitive group of isometries, so homogeneous space, and all the isometries in this group G preserve Q, and that f of Q contains a non-constant function. This is f, not v, right? All right, so that's the generality I want to work in, and see if what I can get out of just these very few assumptions. And so what I want to have is I want to figure out what happens in the case when V was one-dimensional, right? So that was the case I tried to say something about. And they are supposed to look something like this. So we take a homogeneous space M, and we call this a one-dimensional extension if there is a surjective Lie group homomorphism from G onto the additive real numbers. And the kernel has to be so the kernel is H, it contains the isotropy or stabilizer of some point X, where you, that's your sort of base point in the manifold when you write it as a homogeneous space. Okay, so those are, of course, fairly special cases. So then what we can prove is that if you take a G homogeneous manifold and Q is a G invariant tensor, and you have a non-trivial solution F to this equation here, then, well, either you're going to be a product, and so F is supposed to be a linear function on RK, but also it's supposed to be constant on N, or M is this one-dimensional extension that I just described, or it has the possibility of being a mixture of the two. Namely, it could be that it's a product where the factor N is a one-dimensional extension. So you could be in a case where F is constant on N, right? But here F is not constant on N. So that's a situation that you could have also. So that's what you can prove, and without any further assumptions on Q.
Sorry, Peter, isn't 3 a subcase of 2?
Yes, it is. But it is a bit you have more rigidity in 3 than in 2. It's just a special case that's worthwhile pointing out. Okay. So the difference between the two cases here is that you can calculate the dimension of F in all of these cases here, okay? So in case 2, V is one-dimensional, but in case 3, V has bigger dimension, okay? Both V and F. And it's just tied into the Euclidean factor here, okay? That's why we separate it out. All right. So actually, we do need to figure out if we actually have any examples of these one-dimensional extensions. So I'll just mention this quickly. So what the group G has to look like is a semi-direct product, actually. So think H is the kernel, right? So the Lie group structure has to come from some sort of extension of R on the kernel there. And you have some sort of product structure that comes from a map that goes from the reals and back into the automorphism group of H, right? And so this is how you product elements in the group, with S being the real numbers, right? So you have to twist the product inside H using the automorphisms, right? You can, and then you get the projection map. It's just the standard projection here, right, onto the R factor. So now to actually construct an example, the easiest thing to do is that you start with H, but you start with the Lie algebra instead of the Lie group, and you pick a derivation on H. So it's particularly nice if H is not semi-simple, because then you might have even more derivations than you think. And then you extend the Lie algebra. You just construct a direct sum with a real line, and then you extend the Lie bracket to simply be according to the derivation, right? So that's the sort of easiest thing you can do. And from that, you can then create a Lie group G. You can make things simply connected like this, right? So straight from the Lie algebra, you can construct the Lie groups that have this property. And this is basically what they all had to look like, right? All right, so if you take a G homogeneous space that is a one-dimensional extension, right, then G will act in the way that you have this semi-direct product set up, right? So D acts on M as a semi-direct product like this. There is no choice for what it has to look like. And M is going to be diffeomorphic to the kernel of the map you have onto R, mod the isotropy cross R, okay? So the map onto R, right, that just becomes one of the factors. And the metric is special. It's not a warp product metric, but it is just a one parameter family of metrics on this homogeneous space, right? And then on the R factor, it is just the straight sort of Euclidean metric you have on that factor, right? So it's just a varying family of metrics on H perpendicular to the R factor. So that's the metric structure. All right. So now the question is, what more we can say if we assume a little more? So of course, when you have the Ricci tensor, you have a lot more going for you. So I'll just take sort of the minimal one you might have going for you, actually. So if you take a G homogeneous manifold with the Q being this G invariant tensor, and you assume Q is divergence free, then if there's a non-trivial solution to this equation here, then M is a product. And F is a function on the Euclidean factor. So you're sort of eliminating this one-dimensional extension. So you see, this generalizes, of course, the thing Will and I did for gradient solitons in the homogeneous case. All right, so the question is why you assume divergence free. Well, it's because that actually is what happens in the Ricci case. So you have this universal equation, right? This is the contracted Bianchi identity, that the divergence of the Ricci tensor is the differential of the scalar curvature. So if you take a homogeneous space, well, then the scalar curvature is constant, so the Ricci tensor is divergence free, right? So it's a reasonable assumption to make. And so as you can tell, since we do have one-dimensional extensions, it's obvious you need to assume something like divergence free to actually get this rigidity result, right? But to me, it seems like probably the simplest thing you can assume to go back to the gradient Ricci soliton case without making any real assumptions on the tensor involved. All right, so let me just indicate how you get the rigidity. I'm not going to, I sort of also indicated how to prove the original theorem with a one-dimensional extension just by looking at the cases where either V is higher dimensional or one-dimensional, and so you can sort of sort through what has to happen. You have to work a little more on it, but it's not too difficult. All right, let's assume that we want to prove dimension 3 here, and so we want to eliminate the one-dimensional extension. And so we assume we have a one-dimensional extension, and you could actually then prove that this function here that you get from the one-dimensional extension has to be a linear function. So it solves this equation, and it has to be of this form where r is the coordinate you have on the real line, okay? So now what I'm assuming is that the divergence of Q is 0, so therefore the divergence of the Hessian is 0. And if you take the Laplacian of f, right, that's the trace of Q, that's going to be constant then, right? So, okay, good. Now we have to use the Bachner identity in 2 different ways. So first of all, there's a Bachner identity for 1-1 tensors. And it says that if you take the divergence of the Hessian, then it is the gradient of the Laplacian plus the Ricci tensor in the gradient direction. Okay, so that's just one version of it. All right, so the Laplacian is constant, right? So this is just homogeneity. Q was invariant, trace of Q is constant then, right? So that's 0. Okay, the divergence, well, that's the same as the divergence. It's the type change, so that's 0. So the Ricci curvature in the radial direction is 0. And remember, this direction is the r direction that you have, okay? All right, so now we'll use the more traditional Bachner formula, which says that the Laplacian of the norm of the gradient of r squared is the Ricci tensor. Now it's a 0-2 version here, right? But then you get the norm of the Hessian in there, and then you have the inner product of the Laplacian r with the gradient and the gradient, right? All right, so now again, we have that the Laplacian was constant from the previous page. Now the gradient is going to be constant too, right? So what happens then is that most of the terms go away, right? So this goes away, and this goes away, and this goes away from what I just did. And so you can see then that these 2 terms here have to cancel each other, right? So that's the equation I have right here. So, well, but the Ricci curvature was 0. This is even weaker, right, in a sense, because here you're just calculating the Ricci curvature RR. Before it was actually had that this was a null vector for the Ricci tensor, right? So that means that the norm of the Hessian vanishes. Well, then you get a product. And it was the function that gave you the one-dimensional extension that has 0 Hessian. So there's no choice. It was just a product you started with. It's not a semi-direct product. So yeah, so it wasn't really that bad. In many ways, the proof is quite similar to what we did in our early paper, right? It was just sort of extracting all the stuff out that that sort of wasn't useful or didn't have to be used, right? And then seeing what's left. All right, so this has actually had some applications already. I'm not going to define what the Bach tensor is, but it is a tensor that depends on the curvature tensor. It's a little complicated, and it's most useful in 4 dimensions as far as I can tell. And it can be used just like the Ricci tensor to create a flow, a Bach flow that does some interesting things, actually. So what we did, we had hoped that that could be used to some other types of soliton equations, and that has indeed proven true. And so this was done by Erin Griffin. She's just graduating right now, actually. She's Will's student. And so if you take a homogeneous gradient Bach soliton, so this is like a Ricci soliton, but with the Bach tensor instead of the Ricci tensor, well, then you land in our case, but you still have to do some more work. So if you assume it's steady, then it has to be Bach flat. So that's one thing you get out of that, strong rigidity. And if it's not Bach flat, then you get some examples that are products, namely R squared with a sphere and R squared with hyperbolic space. So these are shrinking solitons. So that you get a very strong rigidity for these examples there. And there are actually non-trivial examples. So Ho has shown that these examples do exist. So that was already known before, right? But that really isn't anymore, actually. It's also interesting that there are actually some expanding homogeneous gradient Bach solitons on this fairly simple Lie group here, right? So it's just a sort of an obvious one-dimensional extension of SU of 2. So there's a lot of stuff there to work on. All right, so I want to study the other case too. And this was the one that was related to the conformal Einstein equation, which, by the way, is what Brinkman studied originally in his paper. So he wanted to understand what is the rigidity for manifolds that have two conformally equivalent Einstein metrics. So the equation, as I mentioned, is that the traceless Hessian is this traceless feature multiplied by the function W again and divided by 2 minus n. So you're not studying this in dimension 2, obviously, by the uniformization theorem. That's not really interesting, right? And you can see that this is precisely equivalent to this metric here being Einstein, right? So what you do is you conformally change G with W to the minus 2. And that becomes an Einstein metric if and only if this equation is satisfied. Okay, so that's what we want to keep in mind. And the general case is that we consider the space W of all solutions to this equation, and also the trace-free W with all solutions to this equation. Okay, I skipped the trace-free case sort of in the previous situation. You can do the same thing in that case, in that situation too, but it's not as interesting as it is here maybe. So this is what we can prove. If you take a G homogeneous manifold with a Q being this G invariant symmetric tensor, then if the space W is non-trivial, then M is isometric to one of the following types of spaces. It might have constant curvature that corresponds to W being having maximal dimension. It could be, well, it could be a quotient or just a product of a homogeneous space and a space of constant curvature. That corresponds to intermediate dimensions, or it could be a one-dimensional extension like before, and that corresponds to W being one-dimensional. So those are the situations you might have, right? So this is the intermediate case that we had before. Maybe it makes more sense now that you see it here. But I know I moved them around a little bit here. All right. So again, you might ask if there are any further rigidity things, which does not seem to be so much the case. So assuming that the divergence of Q So this is the equation we're looking at, right? If you assume that the divergence of Q is 0, you don't get any obvious restrictions. So we could actually find one-dimensional extensions that have this property. So there's a big difference, even though the equations look similar. Then there's another interesting equation, namely this. So this is you can see it's very similar to the conformal Einstein equation, but here let me go back so you can see it. Right here it was. This is traceless, but also notice this constant is going to be negative here. Okay. Now, if you go down and look at this equation here, well, I can make it traceless too. If you make it traceless, then this goes away and you have a traceless Ricci there, right? But M here is positive, okay? So they're not really the same. So this is equivalent to the quasi-Einstein equation that Keishu Wei have studied, right? And this is something that Chenzo here and myself and Will have worked on, and also Ramiro. So Ramiro showed that if you have one-dimensional extensions, that they sort of have to look like this, and we showed how you could create some sort of one-dimensional extensions using these types of equations. But also, I guess I have to warn you that it is important that M is positive for all of this to work. Also, lambda should be negative, although I think that becomes sort of automatic. If lambda is positive, it's not going to work anyway. So there are some sort of restrictions on this, what you can do. All right. Now let's go and look at the traceless case. So now I'm looking at the functions where you're looking at traceless Hessian equal to W times traceless Q, okay? So we call that situation essential if this whole space is never equal to W of Q prime for any possibility for Q prime, okay? So there could be some other tensor Q prime because you're just adding some trace to it, to Q, say, right? So that suddenly you would find a G invariant tensor, and then you would just be back in the theorem we already had. So you want to study the case where that could never possibly happen for any reason whatsoever. And that turns out to be special. So if you take a G homogeneous manifold and your favorite G invariant tensor Q, then if it happens to be essential, then it's locally conformally flat. So that becomes very, very rigid because since I'm assuming it's homogeneous, you can classify them. Takagi has the classification right there. Any locally conformally flat homogeneous manifold is isometric to quotients of spheres, Euclidean space, hyperbolic space, products of spheres or hyperbolic space, and real lines in hyperbolic space, and spheres and the real line. So you have to be a little careful how you're allowed to divide out by the groups. So Takaki has 2 papers where he studies these cases. And so one paper he just does sort of what I wrote down here, and then he has another paper I think where he even narrows what the groups gamma can be, because it's not so easy to get a homogeneous space when you divide out by a group necessarily, right? All right. So now, if you remember what 4 and 5 are, so 5 was the essential case, right? And 4 was the case where I assumed I had just a non-trivial W, right? So now what I want to do, I want to study the new situation of the conformal Einstein equation, which is an equation we hadn't studied before. So if you combine the 2 theorems we have there, then you can see that the problem reduces to studying homogeneous, if you want to study the homogeneous case, right? Homogeneous conformal Einstein metrics when reduced to studying an equation that looks like this. Whoops, let's see, this equation here, right? This looks like the quasi-Einstein equation. I've made it now without being traceless, right? And that's because I can eliminate the case where everything is essential as being just the other cases. And so I'm reducing then to the essential case. And then you have to be in precisely the situation when the manifold is not essential, right? So it's like I said, it's like a warp product or quasi-Einstein metric, but with a negative number down there. And so what you want to do is you want to study this, especially on one-dimensional extensions, where you don't have any rigidity. And that's, well, that's a lot of stuff that can happen there, okay? It's not actually clear what should happen. It's not going to be as simple as it was in the quasi-Einstein case, where we know that if it looks like this, you can tell what the structure is and stuff like that. But so there are actually examples, first of all, and there are some classifications. So there's this very recent paper here where they classify the homogeneous conformally Einstein metrics in dimension 4 using the Bach tensor, actually. And they find 3 families of one-dimensional extensions, okay? So it's definitely much more flexible than in the quasi-Einstein case. And you can also see that these families extend to all dimensions. So they exist in dimension 4, but they exist in all dimensions. What we don't know is what further rigidity there might be in higher dimensions, okay? Well, partly because we don't have a useful Bach tensor. The Bach tensor in higher dimensions is not as meaningful, maybe, as it is in dimension 4, as far as I can tell. It doesn't have the same properties. All right, so just to clarify what's going on here. So Ramiro's result, right, was said that a one-dimensional extension is an M quasi-Einstein manifold with M bigger than 1, if and only if lambda is less than 0, and that you have an algebraic Ricci soliton, which is an equation that looks like this. Okay, so I've replaced the Hessian with a derivation here. Okay. And then these examples I had on the previous page show that some, but not all, algebraic Ricci solitons have extensions which are also conformally Einstein. And that there are examples which are not solitons, okay? So the story is different, as I said. So yes, the question, I don't know, does it make sense to say that it's an open question or closed question? If it's a closed question, it's not a question anymore, is it? Actually, somebody once wrote on the blackboard, he had an open theorem. And so we all asked, what is an open theorem? Well, he said, well, I know it's true, but I can't quite prove it yet. That's an open theorem. And then it becomes closed when you have the proof, I guess. So yes, you want to classify the one-dimensional extensions that are locally conformally Einstein. So there you go, Ramiro. Now you have something to work on. It's a
after you showed us theorem 4, I was gonna ask, what about examples? Like something interesting. But
yeah, well, there you go. These are the examples we know, right? That's all we know.
And what are the groups? Which groups show up? Are they always solvable, important?
Yeah, they're solvable, the ones they look at. Well, I mean, I haven't looked at it for a year, okay? So they're all familiar to you, okay? It's nothing super special, but I'm trying to remember if there was something that was reductive. It could have been something reductive too. I think there was, so that you can see that they're not sort of the obvious examples also. But I should have looked at that before I gave the talk. So that's actually it. So just so you can see, right, this is what we studied. The only case I didn't tell you anything about was this case, which really just works like this case. There's something essential, and when it's essential, it's even more special than if it's not essential, right? So that's all you get out of it. So I'll stop there. There are many, many more things one can ask about all of these types of equations and solutions and stuff like that we haven't quite had time to investigate yet.
Thank you.
See, that's why we need to go to Australia again so we can figure this out.
Thank you for a beautiful talk. Are there questions?
Well, I guess the natural question is, what tools does one use to study this PDE, right? I mean, is homogeneity of any help?
Well, I think what we do in this case here, right? It's just the tools are more or less what you have seen, right? And then it's just putting things together and then using all our warp product classifications for some of these things also. So a lot of the rigidity comes out of the earlier stuff we did with Chensu. Okay, so because if you have something like this, right? If you have many solutions to an equation like that, the metric has to be a warp product. So that's what gives you the rigidity. And so essentially what you show is everything boils down to the case when you have just one solution, well, a one-dimensional space of solutions. That's the one-dimensional extensions.
But to actually find one, it's a bit of a guess. Right?
Yeah, I mean the thing is to find solutions. I mean, also the ones we had that were divergence free and stuff like that. You can do this on reductive groups. You don't have to use solvability. So just like one-dimensional extensions of semi-simple groups too. So it's so in that sense, it's quite different from what we're used to.
Peter, about the sorry, are you done, Ramiro?
Yeah, it sounds very interesting. Yeah, go ahead.
Peter, about you said that you generalize the examples in the Spanish paper to higher dimension. Yeah. Is that in a paper?
Oh, I think we just mentioned it. I think it's pretty obvious. I think we just say that they can be generalized.
Okay.
We didn't really want to take credit for it, because it is pretty obvious that the examples exist. That it's the classification that's difficult in dimension 4. Yeah.
Okay. Thanks.
Are there other questions? This is probably a question that can't be answered, but in these cases where the group is actually semi-simple, is there any restrictions known or anything?
You mean the group G? So, well, it's going to be difficult. Usually be difficult to be a one-dimensional extension if the group G is semi-simple.
Right, it's going to be a product. So
yeah, so so that's why it has to be. It can be a one-dimensional extension of a semi-simple group, but it doesn't seem to add anything extra by assuming that.
I see.
Yeah. And of course, the point is we're used to working in the solvable case, so.
Right.
but so we thought, oh, semi-simple, that would be easy, but no, it wasn't. But at least when you generalize this much, right? So.
Mhm. Are there any other questions or? Well, if not, thank you again. It was a really nice talk. And our next talk is in 2 weeks. It'll be by Daniel Thung. And you'll find the time in your time zone if you look on the website.